Okay, so I'm going to switch to exercise number 5. So I want to show that L1 properly discontinuous and free implies properly discontinuous in the sense that I gave. So I'm going to take an x, point in x. I'm going to take k, which is going to be a compact, which is going to contain an open set containing x. Okay, and I know that there exists G1 up to Gn such that for all G, which is not a Gi, G of k intercepting k is empty. So now I'm going to set xi is equal to Gi x for all I. I'm going to take Bi is going to be a small ball open set containing Gi xi for all I, and I'm going to assume that the intersection of Bi and Bj is empty for all I different j, and I'm also going to assume that G1 is the identity, so x1 is my point x, and that B1 is contained in k. Okay, so now I'm going to set ux to be the intersection over these finite number of i's of Gi minus 1 of Bi. And now I claim that for all G different from the identity, I have that G ux intersection ux is empty. So this is immediate if G is not contained in the set G1 up to Gn, since I then have that G of ux intersection k is empty. Now, suppose not. I then have that G is equal to Gi, and that Gi of ux is contained in Bi. Okay, and now this implies that Gi of since I of ux intersection Bi, B1 is the empty set, but ux is contained in B1. Okay, note that the assumption where I said that Bi into Bj is equal to 0 needs xi different to xrj, i.e. it's only possible because G is free. Okay, now I want to go the other way. I want to show that my definition of properly discontinuous implies free and L1's definition of properly continuous. So now, my definition implies free is immediate. Clearly, if I have a little open ball U such that G of U intersection U is equal to is 0, then I can't have any fixed points. And I'm requiring to show now that my definition of properly discontinuous implies L1's definition. So I'm going to say K is compact, and it will be enough to show that for all x in K, there exists an open set containing X such that the set of G such that G Vx into K is not empty is finite. Because if I can do that, then I can cover the whole compact set of, with open sets of this form, take a finite subcover, and I'm done. Okay, so I have this. Now, pick, I'm going to take u of x such that g u of x into u of x is empty for all g different from the identity, and I pick v of x open with x in it such that the closed part of v of x is equal to u of x. Okay, and now I cover u of x, k, with the open sets g of u of x and k set minus the union over g of v of x close. Okay. And I note that since v of x is contained in u of x and v of x and g u of x's are disjoint, this implies that the union of the g vx is closed is the same thing as the union of g vx closed. Okay? Which is contained in the union of g x's, and so this is a covering. I mean, I could have had worries about whether there were not points in this union that were not contained in any of these steps. I could have imagined that I had sequences taken from lots of different copies here, and that doesn't happen. Okay? So now, there exists a finite subcovering which I can assume of the form k set minus union j vx closed, and I got j1 ux up to jn ux. Okay, and now if ji of vx into k is not v'd, that implies that ji of vx into ji of ux is not v'd for some I. This tells me that g is equal to gi, and that is what I need.